Okay, great. So welcome back. It's working? Yes. Great, so welcome back. So we have two talks before lunch. And the first one is by Jérôme, who'll tell us about hydro in an exclusion process with long-range interactions. And we're going to try and keep roughly to time because there's a complicated afternoon ahead of us.
Yes, thank you. So thank you very much. Thanks to the organizers. It's great to be back in this wonderful institute. I think it's really a great place to focus on nice, interesting physics problems with many great people around, and beautiful place. So it's very nice to be back. So I'm going to present some work we did this year and that we put on the archive this summer together with Günter Schütz. So I guess many of you know Günter. He's an expert in stochastic processes, among other things. And Ali Zara, so Ali is a postdoc who did the first 1 year of postdoc with Günter Schütz and then came to work with me. And so this we did the three of us together. So I come from the quantum community, but I'm gonna talk about, this is going to be entirely classical. The reason why I got involved in this is because we are gonna use techniques and ideas that actually come from quantum spin chains. Okay, so let me start with that. So this is about an exclusion process with long-range interactions that I'm going to define shortly. Let me just start with the general background. So as we have already heard many times over the past 10 days, so the general, the colloquial understanding that we have of many-body systems with short-range interactions is that here is a simple example with particles on a lattice that can hop. So that would be, for instance, the symmetric exclusion process, or maybe the asymmetric exclusion process of some exclusion process, for instance. So we have particles on this lattice, they can hop, but there's at most one particle per site. So hopping is forbidden if the site is already occupied. Okay, so we can define a coarse grain density by looking at some interval of length delta x, count the number of particles. This is a stochastic variable, so rho is a stochastic variable, but thanks to the law of large numbers, we believe that or maybe it's proven in some cases, that it converges to a deterministic density. And then the second assumption is the one of local relaxation. So under the assumption of local relaxation, we can also say that the current at position x and time t is the stationary current evaluated in the local stationary state that would have the correct density, correct local density. And then maybe we want to write as something like a gradient expansion of this. And so there would be a first order term that would correspond to ballistic transport, and then a second order term that would be diffusive. Okay, so this we have heard already many times. So now in this talk and in this paper that we wrote, so what we are asking instead is how is the scenario modified if we have long-range interactions? So does this scenario survive if we have long-range interactions? And the specific model that we looked at is what we are calling the symmetric Dyson exclusion process. So let me define this. Long-range interactions. And let me just stress that it's long-range interactions, not long-range hopping. I will explain what this means. I mean, the difference in a second. So this is, again, an exclusion process. And also So it's still a short range exclusion process in the sense that we only have hopping to nearest neighbors. This is still forbidden. However, what changes now is that we have some rates. Let's call them W plus and W minus to go to the right or to the left. And those rates now, the rates depend on the positions of all the other particles. Of all the other particles. So, I mean, in the SEP or in the ASEP, the rates are independent of the configuration of particles, except if there's if the neighboring site is occupied. Otherwise, it's independent. But here, it's the rates will depend on the full configuration. And let me just stress that this is so a remark. This is really different. So this is very different from long-range hopping, different from long-range hopping. Right, so I mean, other people have considered models where it would also be an exclusion process, but you would have particles that would hop to long distances with rates that would scale, for instance, as 1 over distance to some exponent. Let's say this is the distance, this is the length of the jump. So you would have long-range jumps that would decay as with some exponent. So this would also lead to some hydrodynamic equation. I mean, essentially here the particles would undergo Levy flights, and so typically what you would get would be a hydrodynamic equation of this form with some diffusion constant here, and then you would get a fractional Laplacian, this form here. That's if alpha is smaller than some critical value that is equal to 3, and otherwise it would be simple diffusion. If alpha is larger than 3. Okay, so this is also something that you could do, but and something that people have done, but it's not what we are doing. So we are still looking at short-range hopping, just short-range hopping that depends on the position. Here. Well, that's the continuity equation. Yeah, I mean, that's the continuity equation, no? dt rho plus, well, not quite. Yeah, okay. Well, I mean, yeah, I guess this you can still write that d is dx of something, I suppose, but actually I never thought about this. Is anyone familiar with this and know the answer? Can you write this fractional Laplacian as dx times something? But you should still be able to define a current, no? Well, yeah, of course, yes. You have to go to Fourier mode, and this is just k to the alpha minus 1 over 2. But is it then when you go back to real space, is it dx something? Yeah. No, but yeah, that's what it is here. But can you? Okay, anyway, let's discuss this later, maybe. But okay, the question makes sense, I think. I think the connection is fairly straightforward. Okay, but it is just to highlight, just to make it clear that this is not what we're doing. It's different, right? That's long-range interactions, not long-range hopping. Okay. And so the example, we're going to look at a concrete example, and this is going to be this step for a symmetric Dyson exclusion process. So how is this defined? So it's just, I'm just going to write the rates. So the rate for the ith particle at site, let's say it is at site xi. So I have the positions of my particles are xj for j from 1 to n, say on a line. So my rate w plus or minus, and that's for a jump to the right or to the left. We are going to take this in the form 1/2. That's just a convenient normalization factor. And then it's this ratio here, minus plus. From j equals 1 to n, and j is different from I. Okay, so that's for the infinite line. It's also going to be convenient to compactify the line, so to work on a finite system, finite length. So with periodic boundary conditions, and for a system of length L, these W's become so this gets replaced by the chord distance, and the formula then looks like this: minus plus 1 over L divided by sine I xi minus xj over L. J different from I. Okay, everyone happy with this definition? Yeah. Okay, so let me just try to, I mean, why the hell would you consider this? So let me just try to motivate this a little bit. It's a model that Gunther came up with, right? So he knew this model. He has a long experience with it. So the motivations are, there's a few different motivations. So why is this a natural model to consider? One reason, well, first reason, say, is that, and also that's the motivation for the name, is that it's a discrete version of Dyson's Brownian motion. The Dyson Brownian motion. So you know that this is a process that you can define that appears, for instance, in the context of random matrix theory. So if you have positions xi that are now continuous on a continuous line, so you have particles now on a continuous line with positions x1, x2, x3, and so on. Then you can define a process in this way. Like this. So it's a kind of a Brownian motion, but with interactions between long-range interactions between the particles. That is intimately connected to GUE ensemble and so on. So this model here is just a discrete version of this. That's one way to think of it. Yes? Sorry, yes, lambda is x. Yes, thank you. Okay. Well, okay, so another reason why you might perhaps be interested in this is because this would appear naturally if you were thinking of doing a Metropolis Hastings type of sampling of a Coulomb gas on a ring for discrete Coulomb gas. Because yeah, so if you take a ring and imagine you want to sample configurations of n particles on L sides according to the Boltzmann distribution. So exponential minus e of xi with a partition function, where e, you would take e as the Coulomb energy of this configuration of charges. Then one way to do it would be to run this process, and the stationary measure of this equilibrium measure of this process is this Gibbs distribution for this Coulomb gas. So if you were interested in things like mixing times or something of this way of simulating the Coulomb gas, then you would naturally be led to consider this model and its continuum limit and its hydrodynamic limit. Yes.
When local by introducing age, I mean auxiliary variables like age, link variables, like in lattice gauge theory, if you integrate out the age fields, then you have non-local, like Coulomb.
Yes.
So you have originally like local theory, but it looks non-local.
Mm-hmm.
So I'm just wondering whether the reverse can be that here. But if you stick with the local theory.
So you mean you would like to add some degrees of freedom?
Yeah.
And so that if you integrate out those degrees of freedom, then they reproduce this interaction somehow.
It does have.
Well, I mean, yeah, in this formulation, yes, I know how to do it in this formulation. Like you could view those as, for instance, vertex operator in a two-dimensional field theory that would end, and then everything would be local, but in a theory where the degrees of freedom would not be only the positions of these guys, but also the fluctuating field around it. But for the process, I'm not sure what to do with this. But okay. Okay, a third motivation is that you can also think of this as the SEP conditioned to maximal activity. And this is the way that Gunther likes to think of it. To maximal activity. So the way that this arises is that you take the Markov matrix of the SEP, Markov matrix of SEP, which is well known to be the Hamiltonian of the Heisenberg chain. Of the Heisenberg chain, ferromagnetic. So the Hamiltonian, so this is the Hamiltonian of XXX. So we're gonna normalize it like this. So you could write it as this. And then in that model, I mean, in the SEP, in that formulation, the instantaneous current you would write as the operator sigma j plus 1 plus sigma j minus sigma j plus 1 minus sigma j plus, and the instantaneous activity you would write as the same thing but with a plus here. What this means is that the current is the average number of jumps to the right minus the average number to the left on a given link, and the activity is, instead of being the difference of the two, it's the sum of the two. And now, if you want to condition, what you do is that you deform your generator. You're placed by h minus or plus or minus some Lagrange multipliers, say. for the current. Let's call this J and let's call this A for the current and for the activity. So this is something that is well known, that has been looked at by many people, including by Herbert. Herbert, 99, I think, has a paper on this. So Gunther, the paper with Popkov, Damien Simon Schütz, 2010, I think, and other people like, I think this is our German, no? Jack and Solich. This is you, right? Yeah. Also to 2010, then Chetrit, and Hugo Touchet also looked at this. So that's okay. So this deformed version of the SEP has been looked at by many people. The point is, if you condition to maximal activity, which corresponds to taking this Lagrange multiplier here to be very large, then you see that obviously this stochastic, this generator here is completely dominated by this term, and of course this term is nothing but the, and this term is nothing but the XX chain. It maps to a free Fermi model. Okay. Now, of course, so doing this, when mu goes to infinity, you get the XX chain. Now, this is not a stochastic matrix, but you can do what's called a Dove transform to get a stochastic matrix. So this works as follows. So the initial, this means that well, you take the Hamiltonian of this X exchange, and to turn it into a stochastic matrix, you look at its ground state, and then you just multiply. If you take matrix elements sigma, sigma prime, where sigma is a configuration of particles, then just multiply by the ground state. By the component of the ground state wave function, like this, you conjugate by this. This is the ground state energy of the XX chain, and this is the ground state wave function. Ground state wave function of the XX chain. It's the ground state, so thanks to Beron-Frobenius, it's positive, and it has positive entries, and this allows you to define a new stochastic matrix. Okay. And this becomes long range because psi is because I can write the maybe I can write it here. It becomes long range because psi. Let me erase this. It becomes long range because the ground state of the XX chain you can write as this. So it's a Slater determinant because it's free fermions. This is then for A and B between 1 and n. Okay, and this is it's not only is it a Slater determinant, it's also a van der Monde determinant. So you can evaluate it straightforwardly, and this gives you this for I smaller than j. So the components of the ground state wave function are somehow depend on the positions in this way, and this is what then gives rise to the long range to this long range hopping when you do this Dove transform. Okay, everyone happy with this? That's just the definition of the model. Okay. Okay, so now, okay, so what do we get in this model? Okay, so let's go here. So the results that we get. So So the hydrodynamics, so you can get the hydrodynamic equation. So the hydrodynamic equations look like this. So it is, I mean, it remains true that you have a continuity equation like this. But however, it's not, yeah, it's going to be of this form. So you have a continuity equation, but the current will depend on the not on the density at the same point, but on the density everywhere in the system. Okay, and the current takes this form. So you can compute it, and turns out to be given by this. So it's the sine of pi times the density at point x, and then the hyperbolic sine of pi times the Hilbert transform of the density at point x. And the Hilbert transform of a function f is, I mean, here for periodic boundary conditions would be defined as this. So it's the principal value of that integral. Tangent pi x minus u over L. Okay, that's the Hilbert transform. And you see that this term is highly non-local because it depends on this h rho depends at position x, depends on rho at all positions in the system. So in that sense, it's a current that depends on the density in a non-local way. Okay, and so these are the hydrodynamic equations. Okay, so that's the first thing. Now, what's kind of interesting about these hydrodynamic equations is that they come with some limit shape phenomena. And here I wanted to show you some pictures. So can I get the screen, please? Just so that I can show you this limit shape phenomena. Yeah, that's the average current. Yeah. I'm going to talk about fluctuations later, hopefully, if I have time in a few minutes. Yes. Yeah, so this is an illustration of this kind of limit shape phenomena that you can have here. So here, what we consider is just a melting of a block. So we have n particles initially on an infinite line, and we just plot their trajectory. So it's a kind of a Monte Carlo simulation, if you want, or just stochastic evolution, and you see the trajectories. We alternate red and blue just so that we can see something on the figure. So blue here is the trajectory of the rightmost particle. Red is the trajectory of the leftmost particle. But you see that here this is a plot for only 12 particles, and there's some, I mean, you already see that there's something like a shape that emerges somehow where the density is exactly 1, then outside of some region the density is exactly 0, and it looks like there's something that's fluctuating. And as you put more and more particles and you zoom out, it's very clear that there's a shape that emerges like this. So you can compute this shape. So this is on the left is a single block that is melting. you can compute this. It happens to be given. So this red curve here, it happens to be given by the discriminant of some polynomial. So you can compute. And the right is just the similar situation, but with 2 blocks instead of 1. So that's the kind of things that you can compute with this equation. This is just now really a direct comparison with the stochastic evolution. So here it's done for a single block of 100 particles, averaged over 1,000 realizations, and you see that the agreement is the agreement between this hydrodynamic equation and the simulation is perfect. So that's what the hydrodynamic equation is. Now I'm just going to argue that in the following, I'm just going to argue that this is actually nothing but one more occurrence of a complex Burgers equations, which occurs, I mean, is kind of ubiquitous in these type of problems that are related to free fermions evolving in imaginary time somehow, because this is somehow the XX chain in imaginary time. So, I mean, it has appeared in many contexts. I think the first one I'm aware of is in the context of the large N asymptotics analysis of the Harish-Chandra Dubail integral that was done by Matitsin already well, more than 30 years ago now. But it's actually, this model actually is also very close to the PNG droplet model that Herbert has looked at. I don't think they wrote a hydrodynamic equations like this in the paper, but you could. It would be the same equation essentially, except for the boundary conditions. That also occurs in emptiness formation probability problems. There's a super nice paper by Sasha Abanov from 25 where he explains this in a beautiful way. Also, this I mean, Yasser gave a talk last week that was about this type of problems. I guess Dima would also talk about this later this week. And then it's also the same equation that appears in limit shape phenomena in dimer models. And this was understood by mathematicians long time ago. Yeah, I will explain exactly what is the relation now. Okay, so I don't need the screen anymore. Thanks. So why is it the same equation? Yeah, any questions? Well, so this is the one for, you see, this is the one for, no, this form here is independent of the whether it's infinite line or periodic boundary. Here I wrote the Hilbert transform for periodic boundary. If you want to have it for the infinite line, you just take L to infinity, so the tangent is going to go away. This L is going to cancel with this one. Tangent is going to go away, and you're going to get the usual definition of the Hilbert transform. Okay, so why is this? So this is a disguised form. This is a disguised form of a complex Burgers equation. And how do you see this? So the key point is that you can rewrite this this single equation here, this single equation that involves the density in a non-local way. You can rewrite it as two equations that are both local and that are in a sense coupled only through the initial condition. So this can be done as follows. So you can rewrite the two equations as this. No, okay, I didn't explain this right, but okay. this is just, okay. This is, yeah. This is not quite what I wanted to say, but this is just the same equation. And now if you compute the Hilbert transform of that equation, which you can do, Hilbert transform is a linear operation. So you can take the Hilbert transform of this, it commutes with the derivatives. And what you'll find is that this is cosine pi rho, cos hyperbolic cosine of pi rho, like this. And now these two equations here, you can view as the real and imaginary part of I mean, if you define another quantity like rho tilde, that is h rho, then you see that this becomes just two coupled equations for two local quantities, rho and rho tilde. And you don't need to know that they are Hilbert transform of one another, because if they are the Hilbert transform of one another at time 0, then they will remain so at any time. So that's the point. And so then if we define zeta of x t, that is sine pi rho plus I pi times the Hilbert transform. So you know that rho plus in general, if you have a function, let's say a function rho plus I pi times the Hilbert transform of rho is a nice combination because it becomes an analytic function in the upper half plane, including at infinity. So then this thing has nice analytical properties. So you can extend it to the upper half plane, including infinity. And so then you get, this way you get a function zeta of, zeta of z and t. And this zeta of z and t satisfies, you can check that it evolves, its time evolution is this. So this is the complex Burgers equation. Okay. And so now, okay, Jacopo asked about whether this was for the average, and yes, so far everything is for the average. But once you have this, you can also easily get the fluctuations, and if you want the macroscopic fluctuation theory for that system. So the large deviations are captured by what I would call Matizin, because I think he was the first to write it for the continuous case, and then Abanov was the first to figure out how to do it for the lattice case, as far as I know. Let's call it Matizin-Abanov functional. So essentially, you would write a fluctuating hydrodynamic, like a path integral of rho and j. You want a constraint, so you want to impose the continuity equation, as you do in macroscopic fluctuation theory, and then you want to put some action here, and then put the right boundary conditions that you want, that correspond to the problem you want to solve. And the point is that this action here is the integral of minus square root of sine pi rho over pi squared minus j squared dx dt. And this you can, this you can compute. And so this is now the functional that is going to give both the large deviations, and if you linearize around a classical solution to the equation of motion that you would derive from this, which is nothing but this equation, you'll get the fluctuations. And in particular, these fluctuations are Gaussian, and they are given by a Gaussian free field. So fluctuations given by a Gaussian free field. Again, this is not surprising. I mean, it's kind of usual in this Gaussian free field in a certain metric that is fixed also by this quantity zeta. Okay, I don't have time to say more about this. Let me just, since we are over time now, let me just mention two open problems that I think would be interesting to discuss if any of you have some ideas. So one problem, well, I mean, it obviously would be to do this for say, but replacing the XX chain by XXZ, say, so, and there I think essentially we don't know anything. So yeah, so if we were to condition the SEP not to maximal activity but to some other value of the activity, then we would get the XXZ chain. So the Markov matrix in that case would be XXZ. So what can we say? What can we say in that case? I mean, just to define the process itself, you would need to compute those rates, W plus and minus, and those would be given by the ratio of the beta wave function in the ground state with positions like this. So this would be at xi plus 1 to the xn divided by the ground state, the component of the ground state with particles at the same position except for the ith one here. That would be here. So just this quantity, actually, you can think just about this quantity. Looks quite appealing. It looks like it's not, not something that's completely crazy in beta ansatz. Yeah, just doing something, getting a nice form for this seems to be hard. And then maybe another, okay, since many people are from the quantum community here, can we do hydrodynamics of, say, quantum spin chains with long range interactions, and would we get something similar to this, namely a continuity equation with a current that would depend on the density profile in a non-local way. This is, I think it would be interesting to have some quantum examples. So among the things I didn't say is that Kiron Malik, who is not here today, but Kiron and Paul Krapivsky actually got the same. Kiron is here. Kiron is here. Sorry, I didn't see you. Sorry, I didn't see you this morning, so I assume that you, or because Gregory is also not here today, so I assume you were at the same place. Okay, so Kiron and Paul Krapivsky have been doing essentially the same thing, but for the continuous case. So which corresponds to the low density case for us, and then they have the same equation, except you remove the sign and the hyperbolic sign here, but otherwise it's essentially the same thing. And also this Abanov-Matizin equation in that case was known for a long time. Okay, so, thank you.
Time for one or two quick questions.
Hello? Yeah. Actually, just for you to know, like the hydrodynamics in a quantum spin chain long range interaction have been done on linear response, actually by Michael Knappe and the experimentalists in Innsbruck.
Okay.
But they just have like some diffusion equation, but with like instead of having the Laplacian, like the large scale, the fractional Laplacian. So
Yeah, but
that's
that's because, okay, that's probably because
in a linear regime.
that's the fractional Laplacian. So
Yeah.
it's like long range jumps.
Yeah,
That's
but
the case of long range. It's because if you take, for instance, the Heisenberg spin, because if you think in terms of spin language, as long as you have S plus, S minus, long range term with S plus, S minus, then of course it's like long range hopping.
and a model like that doesn't have only also interactions, or no?
It also has on top of it, but I think it's probably
It's
dominated.
dominated by, okay,
Probably it's dominated by the long range hopping.
And what does it happen here if you change the power law in the interaction?
If you change the power law,
Yeah. If you have an idea of what you should expect. Like interpolating between more local and less local. The hopping, like
Yeah.
how the hopping behaves, not the hopping, the interaction, sorry.
Well, I mean, it's probably going to, I would guess that it would be similar to the long-range hopping case. There would be some critical value of the exponent so that if you are beyond that value, then you recover a local equation. But I don't know of any examples.
Okay, thank you.
From Herbert.
So, thank you very much. Very, very nice talk. So I just wanted to add one word on the physical realizations. I mean, you know, this model came up. I mean, this is basically Ted Einstein and maybe other people, but you know, then we started to look a little bit at this model. So you take a three-dimensional crystal and you cut it at a very oblique angle.
Yes.
And then you look at the surface, which is created by this, and then you see that, you know, you will have steps, and basically they are governed sort of, you
That's
know,
the
by this
Wolf
type
crystal,
of model.
right?
Yeah.
Wolf.
That was at the time sort of my motivation to more closely look at the model.
Yeah, these problems have a long history. Also, statistics of Young tableau and things.
I think we should move on to the next
Okay.
one. There's plenty of time for discussion.
Okay, thanks.